Sit beside you.
Thanks for all those who were here for the annual general meeting. For those who just joined us for our presentation this evening. On a Sunday night in the summer. I know there's lots of great things to be doing outdoors, but I think you're going to be rewarded for showing up. Our speaker, Sarah, is a passionate, dedicated advocate for environmental protection and revitalization through the advancement of Indigenous rights and energy sovereignty. They are proud to be of South African heritage and carry forward the legacy of working towards a just and equitable future for coming generations. Through their business, Chromatic Landscapes, they had a 3-kilowatt portable solar energy system built to power on-the-land events that is currently being utilized for their ground source heat pump research that you're going to hear about tonight. They were recently featured as one of 100 women working on the energy transition through the Pembina Institute and Globe Series. Sarah is a master's student in the INRS and a graduate of the Northern Environmental Conservation Sciences degree here at Yukon University. Their interest in energy systems developed through work with the Northern Energy Innovation Team at Yukon U Research Center. They also sit on the board of the Northern Community Land Trust, who are building an affordable and sustainable housing project using a not-for-profit ownership model. Their activities fuel their enthusiasm for ground source heat pumps. Sarah is working to conduct thermal response tests in the Whitehorse area to better understand and characterize the thermal properties of local rock formations. They believe that ground source heat pumps may be the way to provide a stable cost of energy over the long term while reducing greenhouse gas emissions in northern Canada. Thank you for welcoming Sarah. Thank
you so much. Thank you, everyone, for welcoming me back. I was able to present to the Yukon Science Institute in March of last year, and this was my first kind of introduction to the society, although I think I've probably shown up to some lectures that you guys have hosted in the past. So I'm really inspired by this work to share science with the public. And starting with this work takes place on the traditional territories of the Kwanlin-Dun First Nation and Tonquitchan Council. And the purpose of this research is to help our community live in a better relationship with the land and protect our climate for future generations. So these are my 3 kids up berry picking on fish above Fish Lake. And, they're a big reason and motivation for the work that we do. So we know here in Whitehorse that we have a large seasonal discrepancy in energy supply and demand, and our grid is facing increasing pressure to meet these energy needs. We have excess hydro and solar energy in the summertime, and increasingly we're relying on diesel and LNG production to meet our energy needs in the winter. So this graph on the y-axis, we have the gigawatts of energy that we're using, and on the x-axis, we have the months of the year. I think we are meeting about 90% of our energy by renewables over the course of the year. That's I think it's reducing though, because every year we're using more and more diesel energy in the winter time. So this is December, and as we know, in December this year, we were on notice to have rolling blackouts. A big driver of our energy needs in the wintertime is for heating. So this is why I've decided to study ground source heat pumps, because they're highly efficient. For every 1 watt of electricity you use to power a heat pump, you can generate 3 to 4 watts of heat energy. So it's just moving the heat energy from the ground, which stays at a stable temperature all year round, up into the buildings. And they maintain their efficiency no matter what the outside temperature is, which is their real big benefit over air source heat pumps. So this is essentially how a ground source heat pump works, is you have a fluid. This is a closed loop ground source heat pump system. So you have a fluid that flows through the ground, and you'd have these boreholes. and the fluid's going through the boreholes and collecting heat, and then returning that heat to the building in the fluid. And you have the heat pump, which is able to bump the temperature up to the building temperature, so room temperature, 21 degrees Celsius. Now, this technology is really well utilized in other areas of Canada, including Ontario, British Columbia, and Manitoba. However, in Northern Canada, we face some significant barriers to their implementation. One of them is the lack of local data about the ground thermal properties. So the feasibility studies that have been done for the Whistle Bend care home facility, as well as the FH Collins School, we're using a thermal conductivity of 1.5 watts per meter Kelvin, which is how much heat energy is moving through the ground at any one time, like how much heat energy you could actually extract. And this was based on just an assumption. So my research is really trying to address this lack of data about the ground thermal properties. Other barriers include suitable financial models to enable development. So when you build these systems, you're essentially paying for a lot of the energy like up front. It's like making a huge capital investment so that over time, the operating costs are very, very, very low. The energy that you need to run the system is very low, and the maintenance costs are very low. The infrastructure underneath the ground can last from 25 to 50 years. So it's like a very long-term investment, and it's very appropriate for buildings such as institutional buildings. The other last barrier that we have is that we have a heating-dominated load profile. So in other areas of southern Canada, you're using ground source heat pumps for both heating and cooling, which make them really, really useful in areas where you have a hot climate and you have more of a balanced load. So you're drawing that heat energy up in the wintertime into the building, and then in the summertime, you're putting that heat energy back. And unfortunately, we don't have very many days where we need to do that. So that's one of the things, is that we have to ensure that the systems are appropriately sized to manage and recharge over the course of the year from that heating dominated profile. So yeah, again, the purpose of this project is to explore the viability of ground source heat pumps in Whitehorse by characterizing the thermal properties of the ground and mapping these across the landscape. And then the last step is to size ground heat exchange systems based on real heating data from Yukon government buildings. This research is funded by Yukon Government Highways and Public Works. So we're working with them to actually get the heat load data. So when I started this project, I had no idea how complex our geology was in Whitehorse. But it's been really interesting to learn how rocks tell us stories. So we have a sedimentary rock profile like across the landscape. It's very widespread, and it comes from the Mesozoic era. And some examples of this are the Richthofen Formation, which is named after this Richthofen Island here in Lake Labarge. And then we also have Hancock Formation, which is like the Grey Mountain Limestone Formation. So both of those are very big sedimentary rock formations that are across the landscape. And then we also have this really interesting volcanic and intrusive rock history. So, the Miles Canyon basalt was put down, I think I'm not going to get the years right. I'm sorry, my numbers are not going to show up today in my mind. But the Miles Canyon basalt is a really important foundation because that's where our drinking water comes from, and it's really porous, and there's like a lot of water flow. So that's a good type of situation for open loop ground source heat pump systems. And we also have the Whitehorse batholith, which is a granitic rock formation, which I found has a very high, it has a pretty high thermal conductivity, and it's also fairly widespread. One of the other important aspects for ground source heat pumps is understanding the depth to bedrock. So unconsolidated sediments at the surface have a very different thermal profile than the bedrock formations underneath them. So there's a lot of variability in the depth to bedrock across Whitehorse. This is a map that was interpolated by Jeff Witter on the calculated depth to bedrock. So the red areas are the depth to bedrock at 370 meters. And then the purple areas are like where the bedrock is exposed at surface. And then we also have the water table. So when the bedrock and when the sediments are saturated, they also have a very different thermal profile than the dry sediments. So this is a hydrograph of the Cowley Creek monitoring well. And what has been happening in the last 5 years is that the water table seems to be actually climbing in a lot of different sites across the Yukon. So I'm kind of characterizing this as a bit of a staircase effect where every year the water table seems to be getting a little higher. And this is like based on the high amounts of precipitation that we're having, lots of snow in the wintertime. And when that melts and when we get precipitation events in the summertime, the water table seems to be climbing, which is actually good for the thermal property because heat moves quicker through water than it does through just dry sediments. So we have extensive well data from over 1,000 wells available on the YOWN database, which is the Yukon Observation Well Network. These are primarily private drinking water wells, but the drilling logs from all of these different wells give us a profile of the depth to bedrock, of the static water level, and of the location, which is really important. So what I've done is I've taken these water wells and I've paired them up with the Yukon bedrock geology map to understand the bedrock that's associated with these different wells so that I can understand how the water table and how the depth to bedrock is changing across the landscape. When I ran these numbers, the elevation alone explains about 51.5% of the variability in the water table. And the remaining variability is likely seasonal and geological because the static water levels within the wells, the wells would have been drilled all throughout the year. Okay, so what I'm doing with this research, like what I've been talking about, is what the already available data is. So I've collected 45 total samples across Whitehorse with another 5 this year in a different formation. And these rock samples, the rock samples have undergone thermal conductivity scanning in the lab, as well as XRD and ICP-MS geochemical analysis. And then I've also taken 15 sediment samples for needle probe analysis. Further, we have tested the basalt for porosity and permeability to understand how water is going to move through these formations. And the other thing is I've done 8 thermal response tests to date with 3 more planned for this summer. One of them has just been completed. I will explain what a thermal response test is a little bit later on. So this is our lab in Quebec City. This device down here is a thermal conductivity scanner. So what I do is I put the rock samples on top of this scanner, and then there is a bar underneath it, and the bar has a temperature data logger, a laser, and a second temperature data logger. So what happens is as it's moving along, it runs along a planar surface on the rock, and it takes the temperature measurement. It creates a heat pulse by pushing the laser at it, so it changes the temperature of the rock, and then it measures the temperature response. And through those 2 measurements, we're able to get the thermal conductivity, which is how heat energy is moving through the rock, and the diffusivity, which is how it's like a combination of how heat is stored through the rock and how heat is moving through the rock. It's the diffusivity. And we're also able to take porosity and permeability measurements with this fancy device, which is essentially it pumps air, like you put a core of the rock into a container and it pumps air through the container to understand how much pore space is within the container and how those pore spaces are connected, which is the permeability. Now, the last part of my research is to run these thermal response tests, so I'll go over that methodology now. In my bio, I mentioned this building this custom solar trailer. So I have these solar racks set up, and then within the trailer, I have A 3 kilowatt, or now it's a 6.5, I just replaced it. It's a 6.5 kilowatt inverter, a 5 kilowatt hour battery, and then I also have a backup generator. And this powers my heating cable. So the heating cable that's here is my 25.5 meter heating cable. It's essentially like a snow melting cable, and it will inject heat into the ground at a rate of about 10 watts per meter. And then along the length of the heating cable, I attach these temperature data loggers, which are able to measure the temperature down to 0.1 degrees Celsius. I put my heating cable down the well with the temperature data loggers attached, and I inject heat into the ground over 72 hours and then watch the temperature response for an additional 96 hours. So it takes me about a week to run the test. In the 72 hours where the heat is going into the ground, I have to go and visit my site about every 4 to 6 hours. So it's kind of like having a baby, it requires constant attention for that entire time. Because I have to measure, like monitor how much solar energy is being produced and when necessary, run the backup generator. So if the weather is pretty good during the day, I usually don't have to run my generator, but I often have to run it overnight. Yes, Keith? So I try to get as deep as I can. The most appropriate boreholes are boreholes that get into the bedrock, and often they have like sediments at the top and then bedrock at the bottom. The deepest boreholes I'm able to get into in the Whitehorse area are about 100 meters deep, and some of them are quite a bit shallower. So the shallowest I've ever gotten into is about 17 meters deep. And what I did is I folded my heating cable in half in order to do that test. My yes, these are like no drilling. Yeah, existing groundwater monitoring wells. And this is really useful because I'm able to get into them like kind of across the landscape to do a bit of a survey of available drinking water wells or environmental monitoring wells that are appropriate for this type of research.
If you mean some well, the water's going to be moving, right?
Yeah.
And at different rates. So
yeah,
and you're trying to heat something that's moving. It's like turning your hot water tap on and expecting your hot water tank to keep up with it.
Yeah.
How do you like make apples out of apples? Like this is apples and oranges.
Yeah, for sure. So I'm gonna, yes, this is good. Yeah, I'll get to that a little bit more, but yeah, on the next slide, I think. Just give me 1 second. So this is how the thermal profile of the test goes, is like I turn on the test and then I see a very quick increase in temperature and then it slows down. So it's this increase in temperature is actually how the ground is changing. Like the sediments or the lithology temperature is changing. And then I use the infinite line source model and the superposition principle to kind of match these equations. So the dots are the calculated measurements and the green line is my observed measurements. And so these are fitted with a regression. And the late recovery period best meets the assumptions made in the infinite line source model. So that's how I calculate my final like thermal conductivities for each of these wells. And okay, here we can see like an example result, which is where I can get into answering your question a little bit more. So here is the thermal conductivity profile with the depth below the top of the casing here on the y-axis and thermal conductivity along the x-axis. And I've labeled the different types of lithologies with different colored dots. So at the top of the well, I'm in a silty sand, and I can only grab what's been labeled in the drilling log. So these are not geologists that are usually labeling these sediments, but they usually have a pretty good idea of the approximate size of particles, which is where you get the silty sand or the sand and gravel. And the type of bedrock I usually get from the bedrock geology map, or what's expected to be found in the geology there. So this was actually the well at St. Francis Assisi School, or formerly Vanier. So at the top of the well, we're in the silty sand. This has to be saturated sediments. And then you can see where we have the sand, gravel, and the interface with that basalt depth. There's an increase in thermal conductivity here. So this is actually measuring like the groundwater flows, like as the water is kind of infiltrating through the sediments, it's hitting the interface between the sediments and the bedrock, and you can see that increase in thermal conductivity with the groundwater flow. My supervisor, one of the wells that I tested was actually at the cadet camp, and at the bottom of that well, you couldn't even get really like a good thermal conductivity because the groundwater flow was so high. When he saw the thermal profile, which I just showed you here, he was like, that's very typical of just high groundwater flow. So that's how we can kind of tell. When you're looking to model open loop ground source heat pump systems, then the groundwater flow is incredibly important. With closed loop systems, it's not as important. So in an open loop system, you're drawing the water out of the ground, you're pulling that into the heat pump, and then you're pumping it back down. It can go back into the ground, or you could expel it to some outside source. With a closed loop system, you're running something like a glycol or water mixed with glycol at a certain percentage through the system, and it's just collecting that heat energy and going back into the building. The closed loop systems are what we chose to focus on for this research because they're environmentally a little bit more simple. You're not expecting any of that glycol to end up in the ground, and you can also choose to use environmentally safe refrigerants. And so then you don't have to like get a water license because you're not actually pulling any water in or having to deal with the water at the end. But for some areas of Whitehorse, like up through the university where they have really high groundwater flow, like closed loop systems might be like a good, or open loop systems might be a good system. The other thing that you have to deal with open loop systems when you're bringing the water into the ground, into the heat pump, is sometimes there's like corrosion or mineralization that can happen on the heat pump. So it's just a little bit more complicated from a maintenance perspective. You have to make sure to flush that, the corrosion or whatever is happening on the heat pump out at a regular interval. Yeah.
Hold up.
Yeah, absolutely. Especially here we have such hard water. Okay, yeah, and then you can see at the bottom of the well here, we have the basalt formation, the thermal conductivity of the basalt. And then we have edge effects at the bottom and the top of my heating cable. So the assumptions of the equation that we use to calculate the thermal conductivity are not applicable. So it's not it's an unreliable data point there. Okay, so after testing all of these rocks and doing as many wells as I could get into, these are my thermal conductivity results. So this is new from what I was able to present last year. We have the granitic rocks in red, basaltic in orange. The sedimentary on both sides here is in the green and the blue. And then we have the saturated sediments in the dark brown and dry sediments in the light tan. So on this side, we have the in situ results. So you can see the in situ results have like a higher variability and generally like a higher thermal conductivity within the well. And this is because of the fractures and that groundwater flow that we're seeing within those wells. And for the laboratory results, it's just the rock. It's like the small 15 to 20 centimeter sample of rock that I'm able to test in the lab. So we've found that the granitic rocks have a thermal conductivity in the lab of around 2.5 watts per meter Kelvin, which is quite a bit higher than the 1.5 watts per meter Kelvin that were used in a lot of the previous feasibility studies for this technology. The basalt and the saturated sediments have a fairly low thermal conductivity. However, that can be affected by, again, the groundwater flow within those systems. And the sedimentary rocks, this was kind of interesting. In the lab, we found a very high thermal conductivity for the Richthofen Formation, the Mandana Formation, and the Hancock, the limestone formation. However, the one well that I was able to test in the field that is assumed to be in a sedimentary rock formation ended up having a very low thermal conductivity. So I'm going back to that well this year to retest with a longer cable and a higher heat injection rate in order to just verify that this is accurate. We also were looking at the geochemical analysis. So for instance, the percentage of quartz within a rock formation can increase the thermal conductivity. So the mineral profile of these different rocks can have an impact on the thermal properties. So we can see kind of almost a similar profile with some of these like really important rocks with the Richthofen and the Mandana, which are both widespread sedimentary formations. And they also had a very similar thermal profile. This is the pyroclastic formation. Also, like a lot of these rocks, we're finding that they're somewhat metamorphized, which also has an impact on the thermal conductivity, which is probably why a lot of the sedimentary rocks kind of have a bit of a similar thermal profile from what we measured in the lab. And then, of course, the basalt formation, it's highly influenced by the porosity and permeability that we see within that formation. And the batholith had a fairly high thermal conductivity, which was similar to what we saw within the sedimentary rock formations. So within those formations, the granitic and the sedimentary rock formations, we're looking like we have a bit of a global mean of about 2.5 watts per meter Kelvin. And then within the porous formations, which would be the basaltic formations and the saturated sediments, we have a bit of a global mean of about 1.5 watts per meter Kelvin. And this is really important information that we can use in sizing potential ground source heat pump systems in the future. So another really important metric for ground source heat pump systems is the temperature of the ground. And what we do is we use an RBR probe to measure the thermal gradient over the course of the well. So we essentially are lowering a temperature data logger slowly into the well to see how the temperature is changing with depth. And you can see like at the top of these wells, we have a temperature that's being influenced by the air temperature. And then as you're going down into the well, this temperature is not being influenced by the surface temperature as much anymore. And then you're seeing the thermal gradient that is increasing with depth, because we know that I think the global average is about 25 degrees Celsius per kilometer. As you're going down, your temperature is increasing. So the steeper the line, the more the temperature is increasing with depth. So within these 5 wells that I've measured, the average thermal gradient was 21.9 degrees Celsius per kilometer. The measured average for Whitehorse in deeper wells, like going to 500 meters depth, is actually between 26 and 28 degrees Celsius. So that a line is increasing as the deeper that you get. And we're using a temperature between 2 and 4 degrees Celsius for the ground temperature parameter that goes into the sizing of the ground heat exchangers. The only well that I was able to test in Whistle Bend was at the Meadow Lake golf course. Yeah, it's Meadow Lake that's there, right? Yeah. So that one, Mountain View, there, thank you. Mountain View Golf Course. The well that's there is a very small diameter well, and I wasn't actually able to get the RBR probe safely down that well. Like that, it's a $10,000 piece of equipment, and so I don't want to risk getting it stuck down the well. And it would also mean that the well is not useful in the future. So Yeah, I wasn't able to test in Whistle Bend, unfortunately. There was a test hole that was drilled to 300 meters there, and they closed it up. I went to the location, and it was a housing lot, so they decommissioned it. There's a lot of wells like that across the territory. You know, you can find the record on the Yukon Observation Well Network, but then when you actually go to the wellhead, it doesn't actually exist anymore. So there's been a couple of times we've gone around with like metal detectors trying to find these old wells and see if like we can get access to them, but it hasn't been possible, unfortunately. Yeah. So yeah, this is just a measurement of the porosity and permeability of the basalt. So we have about 15% porosity within the basalt samples that I was able to take, and the permeability is what is that? Microdarcies. For about 40 microdarcies. Now, one of the kind of interesting and innovative aspects of the research is being able to use solar energy to conduct these heat tests. So because the cables are 25.5 meters length or 72 meters length is my other cable, my instantaneous heat injection rate is between 250 and 830 watts. And with my solar panels, I was trying to get a measure of exactly how much solar energy I can produce on average in order to meet the instantaneous needs of these tests. So with the 25.5 meter cable, I was able to meet the instantaneous load about 20.6% of the time. So on my site visits every 4 to 6 hours when I show up, is my solar energy matching my heat output? And that's happening about 20.6% of the time. With the 72 meter cable, I was only able to meet the instantaneous load about 6% of the time. So that means that I've had to kind of run the backup generator almost constantly in order to meet the needs of that load. However, this year I doubled my solar capacity. I've now got 4 racks and 8 solar panels. And this week when I was running my thermal response test during the day, I barely had to run the generator at all, even with our kind of crappy weather. Like it's been raining a lot, and I've still been able to kind of meet most of the needs of the test with solar energy. The other really interesting thing about using these solar racks is I can chase the sun. So we know the sun is kind of like running around us in a circle. And most of the time, the solar panels that we have like installed on rooftops and everything, they're in a static position, usually facing south. But with these panels, when I show up at my site visit, they're often producing just a little bit of solar energy. So the blue bars are when I arrive at site. And then I pivot the panels to try and optimize the amount of solar energy that I'm getting. And I'm able to produce hundreds more watts with the use of these like portable panels. So this, I think, is relevant and interesting here in the north because it's, you know, if we're looking to use solar to try and meet more of our energy needs, like being able to like rotate the panels, it would be like really important. The solar project in Old Crow, they've actually oriented their panels in an east-west direction to really optimize the use of that like sun energy that's kind of traveling around. So yeah, even here at the lower latitude, this is like a really important aspect of using solar. Another improvement to my system I've made is I've been able to install a device that actually gives me an instantaneous readout on the internet about how much solar energy I'm producing, as well as the state of charge on my battery. So this is kind of what's happening. I can like pull up my phone and I can see that the solar energy is right now is like 835 watts. It's charging the battery at a rate of 711 watts, and I had a 100-watt load on the system at the same time. So when I set up the Starlink, I can actually monitor the system remotely and maybe get a little bit more sleep when I'm running these tests. So what's happened now is I've created these neighborhood level assessments. So based on all the data that I've just given you right now, is I've gone neighborhood by neighborhood, looking at the major rock types, looking at the thermal conductivities I was able to measure, and looking at the data from the wells that are in those locations. like especially our rural neighborhoods where there's a lot of drinking water wells that have enough data to interpolate how much, like where the water level is at, what the ground elevation is, and what the depth to bedrock is, and the variability. So the light colored bars are the variability, and the dark colored bar is the average. And I have created essentially a table of the expected thermal conductivity, average thermal conductivity at the different locations to 150 meters, which is what we would expect to have for the ground heat exchangers. So the neighborhood that came up on top was Canyon Crescent and Ravens Ridge with the 2.6 to 2.5 watts per meter Kelvin. This is where the bedrock is very close to the surface. And then the kind of like losers of my, well, they're not losers. The ground, like Golden Horn, the area with the sedimentary rock is looking at like 1.64 watts per meter. And Riverdale is again 1.74 and 1.73 watts per meter Kelvin, depending on the type of bedrock that we're expecting in those locations. You know, yeah.
So Riverdale, would you think because there's quite an active aquifer under there, is that why maybe that it would be lower?
So with those, it is the porosity means that the thermal conductivity is fairly low for the basalt formation. So the groundwater flow is going to have a higher impact on the thermal behavior of the ground heat exchanger in that specific neighborhood. The way that you'd actually model how that works is with numerical modeling, which I have not gotten into as far as my master's degree. If I do a PhD, it's probably going to be about that. Yeah.
And so Golden Horn is up on a like, is that like in Golden Horn subdivision? Is that?
Yeah, so what I'm seeing here from the table is that the dry sediments are really deep there. So the water table is low. The water table is really far down. So in that case, you'd have to drill really deep in order to get like an appropriate length of ground heat exchanger in there. Because you wouldn't be able to put the ground heat exchanger in the dry sediments. It's just not going to transmit heat very well at all. Yeah.
But you see Golden Horn 1, it has the same 66.
Oh, sorry.
It has the same 66 as 31. Saturated sediment, same. It's the same, but then it's 175.
Because the type of bedrock is has a higher thermal conductivity than the sedimentary. Yeah, granitic, yeah.
The well in Porter Creek.
The wells that I pulled this data from are from the Yukon Observation Well Network. So it's from any drinking water wells or any other wells that have been drilled that have their drilling logs stored in that. So many of the wells in Porter Creek are actually related to environmental monitoring around the industrial areas, for instance. So we pull data from those wells as well. It is just beside like Marwell and the Mount Sema subdivision. It's just like this little tiny band of houses there. Yeah. Again, the data that was used to create this was all data that I could pull from the Yukon Observation Well Network. So I don't think that there was very many wells in Hillcrest, but wait, no. Hillcrest, I counted all of the wells from the airport area. So we're looking at those wells as well as any other wells that were like up on the hill from the tank farm and everything like that. There's like a bunch of wells that have been drilled again for environmental monitoring purposes. So I'm pulling data from all of those wells. I'm sorry, I haven't memorized the location of all these wells because there's over 1,000 of them. Yeah, for sure. There are many wells, and again, some of the wells that I'm able to access the data, the well the actual well doesn't even exist anymore. You wouldn't be able to see it on the landscape, but we have the data from it from the drilling logs that have been uploaded. Water Resources Branch went to the major drilling companies, including Cathaway Resources and Midnight Sun Drillers, and like essentially mined all of their drilling logs in order to put the data onto the website for the public to be able to use. It's a really, really great resource if you're having to look at water wells. Any other questions? Okay. All right. So in my results, we've realized that the thermal conductivity of some of the bedrock formations is definitely higher than what was used in the feasibility studies that have been used to kind of assess the feasibility of some of the proposed ground source heat pump systems in the Whitehorse area. I think that's a really significant finding. Where we have low thermal conductivity, including sediments like in the airport area where there's like a lot of sand and sediments like that, there is the potential for borehole thermal energy storage, which is a way to actually seasonally store energy. The low thermal conductivity means that there's a high resistance, so that heat energy could get stored in the ground. Unfortunately, you're going to lose about 40 to 50% of the energy. That's like the efficiency of those types of energy storage systems, but they are seasonal, which is one of the things that we're kind of lacking, is the ability to seasonally store energy. So, and what we've done is narrow the range of expected ground temperatures to reduce the uncertainty in ground heat exchange calculations, which is also really significant. And this is across the landscape, not just in specific locations. And the neighborhood assessment, so the document that I have that kind of outlines all my results and goes neighborhood by neighborhood to assess the feasibility. This is undergoing review right now, and I'm hoping to upload it to the open files from the Yukon Geological Survey in the fall. And this is a really important resource that I'm hoping to leave for future designs of ground heat exchangers. It's the type of document that somewhat like a mechanical engineer could pick up and use it to help them size a ground heat exchanger for specific buildings into the future. And so the next steps in this research is I'm going to take these results that I've got for the neighborhood assessments, and I'm actually going to size ground heat exchangers for the St. Francis Assisi School under some different conditions. And I'm also going to size it for a like essentially an archetype building from Energy Plus, which is essentially what a school would be built at if it was built at today, the energy standards and everything that we have today, to find out what size of ground heat exchanger you would need. So this is like how many boreholes at 150 meters deep, like what's the size of the bore field that you'd actually need to build in order for these systems to be viable. My funder, Jeff Quincy at Yukon Highways and Public Works, thinks that institutional buildings such as schools are our best case scenario for implementing these systems, because they can, like with a big project like that, the budget is already so big that trying to like adding on the expense for buying that energy up front could be like a smaller ask reasonably. And the other thing is, like, you know, when a school is coming up for a major mechanical system upgrade, that's again another opportunity where we have to try and implement these systems. Some buildings are built with boiler systems or low temperature boiler systems, and these are the types of building mechanical systems that would be like suitable for a retrofit, where you could add a ground heat exchanger to help improve the efficiency of that system. These ground heat exchangers could definitely help meet like the base load energy over the course of the year, but we expect that you'd still need some kind of auxiliary system and a backup system to meet like peak loading in the middle of winter. They would be really beneficial, say with biomass, for instance. Like you could have a boiler that was like fed by ground heat exchanger most of the year, and then you use boiler, like a biomass boiler, to bump the temperature up in the middle of December when we have like a really low load. And that would help ensure that we're not like drawing the ground temperature down too quickly, because that's the risk, is that if you don't size the system appropriately, then you can like draw the ground temperature down, and then you have to let it recharge for however many years in order to use it again. But it would still be renewable, right? You'd still be able to turn it on, but you just might need to either adjust the temperature settings so that you're not drawing so much heat energy out of the ground every year. And then again, we're continuing monitoring the use of solar energy for this specific application, which is a heating load. It's a constant heating load. So this has been something that I reported 2 weeks ago at the World Geothermal Congress. So Jean-Ethan, thank you. Merci. Do you have any more questions?
So with the data that you're collecting, everything that you're collecting, obviously the density of the distance the holes are apart, I don't know what to call them, thermal wells. Anyways, and the depths and all that kind of stuff. Because for a home or school, it doesn't matter. Your amount of real estate that you have available to put these holes in. So your data will be able to calculate that.
Yeah.
You can't have them too close together.
No. I think the rule of thumb is that the boreholes should be 5 or 6 meters apart. Yeah, but my colleague in this research, my research group specializes in geothermal energy. So I have colleagues working on northern communities all across the country. So one of my colleagues is working in Northwest Territories, and his modeling actually expected that you'd need to put more distance between the boreholes to reduce that they call it thermal interference between the boreholes. Yeah, so that's really important. When you put the parameters that I was talking about today into a ground heat exchange software, because there is like these programs that run the calculations that you need in order to size these systems, you take into account the distance between the boreholes and the size of the bore field. Yeah. So
for the average, especially the smaller lots and the size of buildings in residential, there might not be enough room to put. Well, I guess you can put them underneath your old feet. Yeah. Jeff Quincy doesn't think that there's a real good market for ground source heat pumps for individual residences because of that very reason, for one. For two, the economies of scale. It's very, very expensive to drill. And for one person, like one family, to be putting that into their home, that probably doesn't make sense. And the third reason is that the houses that we build here in Whitehorse are some of the most energy efficient in the country already. Like that's the city bylaw, is that we're like building to tier 4 or 5 on the national building code energy like categories that they just put into place. So like we don't actually need a lot of energy to heat our buildings because of how energy efficient they are. But it does make more sense for institutional buildings, for commercial buildings, and potentially for multi-unit residential as well. Yep.
I'll take you up on that domestic way of doing things. I was thinking of my place, just drilling very shallow stuff. This is generally very easy. And just peppering the ground. And because I'm on solar and I don't use hardly any of it during the summer, I was thinking, well, maybe I can shove 12 kilowatts an hour down during the day for 3 months, and I create a bulb of heat. Yep. Low conductivity shouldn't disappear, but you said roughly you lose 50% of your energy. Yep. I turn that around, when I suck that out of the ground, I've got like 288 days of 20 kilowatts. Yeah, for sure. So that's quite a lot. Yeah, I'm all for it. And there are some private residences around Whitehorse that do have ground heat exchanger systems. Like there's a farmhouse that is using a shallow horizontal system, and they're able to heat like quite a large house with this ground heat exchange system. And they're lucky that they're on a farm. They have a lot of space. They've utilized a big area in order to run this
this heat exchange system, and they utilized a company out of Alberta to come up and install this and a monitoring system for them. But it is viable. And I know of another project where she's putting a ground heat exchanger actually into a lake that they have within their neighborhood, and that's also like a very interesting way to use ground heat exchange systems. The Taku River Tlingit First Nation has one of those systems for their administration building in Atlin Lake. So yeah, there's like a lot of different ways that you can utilize it. I think like in your case where you have so much solar energy and you're not utilizing all the solar that you have, like that's a really great idea to do it. And as long as you have like again, the saturated sediments are what you're looking for with a low groundwater flow in order for that borehole thermal energy storage to work best for you.
I think it is feasible.
Yeah. Yep.
Another question for you. The temperature of the ground that you had there was at best 4 degrees centigrade.
Yeah.
It's not going to take a lot.
No.
To make that frozen.
Yeah, so with the depending on the percentage of refrigerant that you have within your mix, you could actually get the ground temperature down to about -7 degrees Celsius and be able to still pull energy out of the ground with the glycol. So that's one of the things that creates that dynamic. And at 150 meters depth, then you're going to get a little bit warmer than that. Some areas where like in Porter Creek, there's a couple of warm springs where you're actually getting like 16, 17 degree water coming out at surface. So, yeah. Mm-hmm.
So is that then recharged
Sorry.
from the ground up, or is it recharged from the ground?
This is the system in Porter Creek is not very well understood. The heat energy that's coming from that system is theorized to be from radiogenic heat production from local granitic rock formations. These are fairly young granitic formations that have radioactive elements that are actually producing heat energy. And it's the same type of formation that we have in the Tahini hot springs. So they're theorized to be the same type of system, and we know that these exist in very localized areas, at least those 2 locations around Whitehorse. So, yeah, yeah.
I know of a school that outside of the Yukon that uses thermal heat under their soccer field.
Yes.
But I would like you to answer a little bit about what does the land trust do? And then also, it's possible at 20 kilowatt hours that per day, that would recharge an electric vehicle. So there might be an application besides heating homes. But anyway, I'm curious, what's land trust doing?
Yeah, so the Land Trust is a nonprofit housing developer, and we're just completing the first building of our 32-unit housing complex in Whistle Bend. And that project helped inspire me to conduct this research because I started looking for some alternative heating options, especially in Whistle Bend for our units. The research that I've ended up conducting did not really align with the development schedule of the Community Land Trust. So that building has more conventional heating sources in it, but yeah, we're doing Haynes Junction next. That's our next project, and there's some interesting potential in Haynes Junction for ground heat exchangers. Yeah.
Whitehorse have a regulatory framework for it?
Not yet, no. What we would be relying on is the regulations that are related to water wells. That's kind of the essentially the existing framework. And Emily Janin at Strategic Initiatives in Energy, Mines, and Resources, she's working on regulation relating to geothermal in general across the territory. So I've talked to her about trying to include the use of ground source heat pumps within that regulatory framework for the territory. One of the important aspects for ground source heat pump specifically is like understanding who like owns and controls that thermal resource, because you could imagine if you had like a whole bunch of ground source heat pumps that went in at the same time, that they could really start influencing like the ground temperature in significantly. So like that aspect of heat energy needs to be regulated. Unfortunately, from a regulatory framework, I think they're more interested in geothermal energy for electricity generation, or like deep geothermal, which is like 1 or 2 kilometers down, even if that was for like district heating systems.
That's highly.
Well, yeah. Right now, the federal government has put a lot of energy, a lot of money into Arctic sovereignty, including energy sovereignty and infrastructure to support Department of Defense. And Whitehorse is one of the communities that's kind of come up on their list as a potential for future development. And geothermal is one of the potential types of investments that they could make. So it's not out of the realm of possibilities, but.
You've emphasized permeability.
Mm-hmm.
Fracture control.
Yes. So this is an area of my research that I haven't developed a lot of expertise in yet, but we are considering it as something that is like, you can see in the data that it's significantly influencing the experience thermal conductivity from the thermal response tests. So this is like definitely an area for future research, is to really look into that. Yeah. Again, I think that would be like more numerical modeling is how you're kind of like looking at how the fracture systems are expected to work and how water is flowing through those systems. And for that type of analysis, you'd be looking at you'd want to look at a specific site. Yeah.
Good. Well,
Thank
looks like
you very
that's
much for
yeah,
your
thank
interest
you.
and your questions.
Thanks, Sarah, and thanks everyone for being here and the great questions. We're lucky to have Sarah here doing this work. We'll have to have her back again and get a sense of what the sizing would look like for that school, to have some more data, which gets us further down the road, I guess, of feasibility. So join me once again in thanking Sarah for her presentation today.